All right, welcome to the next video covering our look at exponential functions. Today we're covering topic 3, exponential functions. So here's the standard that we're looking at. We want to be able to construct, in this case we're looking at exponential functions, including geometric sequences. And we're going to be looking at those given a graph, a verbal description of a relationship, or two input-output pairs, such as reading these from a table. So that's what we want to be getting at today. As an objective, what we really want to focus on is this over here. We want to be able to write equations of exponential functions. All right, so let's review what we know about functions. Functions can be written and represented 4 different ways: as verbal descriptions, so we can describe the situation that's occurring. We can look at equations using variables. We can put those functions into tables, and we can put those functions onto graphs to see the relationship. And what we're going to look at today, we're not going to look at quadratic functions, but we are going to review linear functions and introduce exponential functions. So let's talk about linear functions. First, let's take a look at an example and understand why it describes a linear function. So verbally, this is being described as a situation where you're driving to visit your best friend in Gulfport. Since you have a long drive ahead, you turn on your cruise control, and the cruise control keeps your car traveling at a constant rate of 60 miles per hour. So what makes this situation a linear function is the phrase right here, constant rate. And that constant rate that you're traveling is, in this case, 60 miles per hour. So then we can take that description and we can write an equation where we're comparing the two things that we're comparing are the number of miles and the number of hours that we're driving. So since the distance in miles depends on the time, that's my function. So the miles are a function of the hours. And so miles is represented by f of h and hours is represented by h. So as an equation, we're saying that the number of miles, f of h, is equal to 60 times however many hours we're driving. Because we're traveling 60 miles each hour, we're traveling 60 miles times the number of hours that we've driven. So if you think back to what we learned about linear equations, we could always write a linear equation in the form of y equals mx plus b. Right? Y was our dependent variable. The m value was the rate of the situation. X is the independent variable. And the b value, the added value here, is the starting point or the initial value. All right, so in this particular case, this equation, f of h equals 60h, is in a linear equation. F of h, the number of miles, is the dependent variable. 60 is the constant rate that we're traveling. The number of hours is the independent variable. And notice there's nothing else at the end. It's plus 0 because we're starting at 0 miles. Right? When the time is 0, we haven't started driving, so we've covered 0 miles. And every hour after that is 60 miles further. All right, so f of h equals 60h is, in fact, a linear equation in y equals mx plus b form. Now, what does that look like in a table? Well, over here, we've got our hours. And here, f of h is our miles, right? So the table is showing every hour. So after every hour that we drive, we're increasing the distance by 60 miles. So we're adding 60 miles every hour that we drive. Okay. And if you think back to the last video on arithmetic sequences, remember arithmetic sequences used addition just like this. Okay, so that means that this linear function here is an arithmetic sequence with a common difference of 60. Okay, so you see how all of this ties together. And arithmetic sequences, what we learned last time, was that they graph as a straight line. Okay? And we also knew that from before, where a constant rate of change, in this case our 60, that's our rate, that because the rate of change is constant, our graph is a straight line. And you can see the graph shows that every hour we're traveling an additional 60 miles. In 1 hour, we're at 60, 2, 120, 180, 240, 300, 360, and 420, and we could keep going and going and going. Right? But every hour is another 60 miles. Okay, so that's a quick review what linear functions look like as an equation, a table, and a graph. So now let's introduce exponential functions. Exponential functions, here's an example up here as a verbal description. You're performing an experiment in science class in which you start with 100 bacteria and the amount of bacteria doubles every hour. So this is a key phrase here. Doubles tells me we are multiplying by 2. And since we are multiplying by 2, that makes this description here a geometric sequence. The number of bacteria has a common ratio or a common factor of 2. And we learned that geometric sequences were exponential. So that's what makes this a description of a exponential function, because the amount that we have is doubling each hour. So as a table, what does that look like? Well, at the beginning here, we start with 100 bacteria, and then it's doubling each hour. So for that first hour, after 1 hour, it increased by a factor of 2, so from 100 to 200. The next hour, 200 doubles to 400, then 800, 1600, 3200, 6400. So each hour we are multiplying by 2. And again, that's what makes this a geometric sequence, the multiplication. If we were to put these points on a graph, right, you would see that the population starts slow, and then once it reaches a certain point, it starts increasing very, very quickly on our graph. Right? And this is what an exponential graph looks like. It starts a slow increase and then a sharp curve once it starts moving further along. So now we need to explore and understand, how do we create an equation for an exponential sequence or an exponential function? So here's the steps that we're going to follow. First thing we need is 2 points from our graph or from our table. And here, this key is, it's helpful to use the y-intercept. Well, what is the y-intercept again? Just to review, the y-intercept is where x is 0. Okay, the y-intercept is what y is when x is 0. We also want to use the coordinate where x is 1. So looking at our table, those 2 points where x is 0, at time 0, the number of bacteria from our table is 100. So we're going to use the point 0 and 100. Then we're going to use where x is 1. So when x is 1, at 1 hour, it doubled, so we're up to 200 bacteria. So this is my x and y terms. X is 0, y is 100, x is 1, y is 200. And now they give us just like linear equations have a specific equation that we use, exponential equations also have a specific equation. And it's this: y equals a times b to the x power. Okay? And this is why we call this an exponential function, because x is an exponent for this function. Okay? So just like for linear functions, right, so linear functions used y equals mx plus b. Right? Exponential functions, we're going to use the equation y equals a times b to the x power. Okay. So now what we need to do is we need to figure out our values for a and b. We want to find what a is equal to, and we want to find what b is equal to for this situation. All right, so I'm going to use my x and my y coordinates to help me with that. So first, I don't know what a or b are, but I do know what x and y are. So first, I want to use my y-intercept. When x is 0, y is 100. So I'm going to rewrite this equation as 100 for my y value is equal to a times b to the power of x, and in this case, x is 0. So this is, you can hopefully see why we use the where x is 0. Because what do we know? We know that anything to the power of 0 is just 1. So I can replace b to the power of 0 with 1. So I've got 100 is equal to a times 1. And a times 1 is just a. So by plugging in x is 0, y is 100, I found that a in my equation is 100. Now we know what x, y, and a are. We want to figure out what b is. So now we need to use the second point. X is 1, y is 200. So I'm going to use y equals a times b to the x again. So y is 200. That's equal to a, I now know is 100. So I replace a with 100 times b, and x now has become 1. So it's b to the first power. All right, so let's think about this. Anything to the power of 1 is just itself. So b to the first is just b. So now we've got 200 equals 100 times b. And I'm going to solve for b by dividing this side of the equation and the other side of the equation by 100. So 200 divided by 100 gives me 2. So that means that b is equal to 2. So I use those 2 points to figure out what a and b are for my situation here. So I found a is 100 and b is 2. So now we want to substitute a and b into the equation. So I'm going to go back to my formula here. Y equals a times b to the power of x. And I'm going to replace a with 100 and b with 2. And so my overall equation will be y equals 100 times 2 to the x power. Okay? And you can test this equation to make sure that it fits with the table that we have over here. Okay? If we replace x with this column here, right, this is x. If we replace x with these numbers, we should get these y values in this column. So let's take a couple just to figure this out. So we already know 0, 100, and 1, 200 work. What if x is 2? Well, if x is 2, right, y is equal to 100 times 2 to the second power. And 2 to the second power is 4. So y is 400 when x is 2. And notice that's what we have here in the table. X is 2, y is 400. What about if x is 3? Y equals 100 times 2 to the third power. 2 to the third power is 2 times 2, which is 4, times 2 again, so that's 8. And 100 times 8 is 800. So when x is 3, y is 800, and it works. Okay? And it would keep following the same pattern. So this equation that we came up with was true. Y equals 100 times 2 to the power of x. All right, so let's practice a little bit more. All right, so here we're given just a table of values, a graph, and we want to write an equation for the exponential function. So for each of these, so for this one here, we want to use the equation y equals a times b to the x power. because they've told me that this is an exponential function. So I want to use the exponential equation. All right, so I need to use 2 points. The first point that I'm going to use, which we said, was to take where x is 0. So that's this point here. X is 0 and y is 4. We also want to use where x is 1. So x is 1 and y is 12. So this is going to be the first point that I use, and this is going to be the second point that I use. So for the first point, we want to take y equals a times b to the x. Right? So we use our equation, and we're going to replace x with 0 and y with 4. So if y is 4, I can say 4 is equal to a times b to the 0 power. So I replaced y with 4 and x with 0. And just like in the last one, we know that anything to the power of 0 is 1. And so 4 is equal to a times 1. And a times 1 is just a, so 4 is equal to a. So now I know a is 4. Now I'm going to use my second point. X is 1 and y is 12. So if y is 12, that's going to be 12 is equal to a, which I now know is 4, times b to the first power, which b to the first power is just b. So 12 is equal to 4 times b, divide by 4. So b is equal to 12 divided by 4, which is 3. So now I know what a and b are. So my equation that I can write is that I'm going to go back and use y equals a times b to the x. I'm going to leave x and y as variables, and I'm going to replace a and b with what I found here. So y is equal to 4 times 3 to the x power. Okay. Now what I want to do is I want to look at this equation, and we want to come up with a hypothesis. What do we think the a term is telling us in this equation? All right, let's think back to when we talked about linear equations. Right? When we had y equals mx plus b, we knew m represented the rate or the slope of the line, and b was the y-intercept. Okay. We want to do the same idea here. What is a telling us in this equation? Use blue. What is a telling us in this equation? A is 4. Where else do we see 4 on the table or in the graph? Well, here's 4. 4 is when x is 0, right? If we look on the graph here, 4 is when x is 0. And what do we call the point on a graph where x is 0? We call that the y-intercept. So it looks like the a value in my equation, in my exponential equation, is the y-intercept of my graph. Okay? So looks like when x is 0, y is equal to a. Now let's do the same thing for the b term. In this case, b is 3. Well, where am I seeing b in this relationship here? Well, how am I getting, if x is 0 and y is 4, then x is 1 and y is 12, what have I done? To get from 4 to 12, I've multiplied by 3. And from 12 to 36, multiply by 3. 36 to 108, multiply by 3. So it looks like the b term is telling me in an exponential equation, the b term is my common factor or ratio. Right? It's the number that's being multiplied. It's my multiplier. It's my common ratio in, for example, a geometric sequence. Right? It's the number that is increasing, in this case, increasing the y term. Right? So the a term in my equation is the y-intercept, and b is the common ratio or the common factor on the graph. All right, so now I want you to try it. Write an equation for the second one here using this table. So you're going to want to use the 2 points from the graph. So you want to use where x is 0 and where y is 1. And you're going to want to write your equation using the exponential equation here, y equals a times b to the x power. So go ahead and pause the video and write an equation for this exponential relationship, this exponential function here, and then see if our hypothesis holds true. Does a equal the y-intercept? Does b equal the common ratio? All right, so you should have hopefully gotten the equation this way. So we're using x is 0, y is 2 first. So as we want to know what a is and what b is. So y first is 2, and that's equal to a times b to the power of x, and y is 2 when x is 0. So 2 is equal to a times b to the power of 0. And just like before, anything to the power of 0 is 1. So it's a times 1. And a times 1 is just a, so 2 is equal to a. So my a term for this exponential equation is 2. Now to find b, I need to put a into my equation and use a different point. So in this case, I can use 1 and 1. So y is 1. That's equal to a now, which is 2, times b to the first power. And b to the first power is just b. So now if I want to solve for b here, I need to divide by 2 on both sides. So b ends up being 1/2. Okay. So my final equation, if I write this as my equation here, let me get it the right color. There we go. All right, so y is equal to a times b to the x. So y is equal to, now I know a is 2 times b, which is 1/2, to the power of x. So this should be my equation. So now let's see, did the hypothesis that we came up with on the previous one work for this equation also? A is equal to 2. Right? So we thought before that that meant that a was the y-intercept. So does that work? Is 0a the same thing as what I have in the table? And it is. You see here? A is 2, y is 2 when x is 0. So a is the y-intercept of the graph way down here. Right? B, we said, was the common ratio or the common factor, or how we were changing the y term in our table. And is that what we're doing? 4 times 1/2. If I do 4 times 1/2, that's 4 times 1 over 2, which is 4 over 2, which is 2. So 4 times 1/2 makes 2. If I multiply 2 times 1/2, that's 2 over 2, or 1. So that's how I got to my next term. I multiplied by 1/2. 1 times 1/2 is just 1/2. So the pattern seems to be working. That b term that I found is what I'm multiplying by to change my y value. Let's do it one more time. 1/2 times 1/2. Well, that is, in fact, 1/4. So we can see that both the a term and the b term worked. A is the y-intercept for our exponential equation, and b is the common ratio, or how I'm multiplying the y term to get each time I move along the x-axis. Right? One more thing to look at comparing these two things. Notice here we're multiplying by a number 3, over on the left, we're multiplying by 3, and the graph is going up, right? Here, we're multiplying by 1/2, and the graph is going down. Okay, so keep that in mind as we move forward. What causes the graph to go up? What causes the graph to go down? All right, so I want you to pause the video and work through these 4 equations. These are 4 exponential equations. Match them to the different graphs that are shown here. All right, so pause the video and then come back and we'll go over your answers. All right, so let's take these one at a time here. So remember, the whole thing is that we're using y equals a times b to the x power, where a is the y-intercept of the graph, and b is the common factor. So we're going to take each of these. We're going to start with f of x is equal to 3x. So f of x equals 3 to the x power. So I want to write this so that it's in y equals a times b to the x. So I'm going to replace f of x with y. Okay, and 3 is to the power of x. So what is in place of my a term here? Well, if there's nothing there for a, just assume that it means 1, because 1 times 3 to the x is still 3 to the x power. All right, so in this case, I'm doing y equals 1 times 3 to the x. So looking at that equation, my a term is 1, and my b term is 3. So if I look at these 4 graphs over here, which graph matches a y-intercept of 3 and a common factor, a y-intercept of 1 and a common factor of 3? All right. Well, looking here, this graph, no, it doesn't cross the y-axis at 1. The first graph, there's 1. All right, there's 1, so that graph doesn't go through there. 1 is here, so that one's close, but not quite. But this one, yep, this one goes through a equals 1. Okay. Now let's double check. Common factor of 3. So if I start with 1, right, so if I start with 1, to get to my next term, I'm going to multiply by 3, so it should be 3. So the next point on my line, when x is 1, I should be up here at 3, which I am. Then I would do 3 times 3, which is 9. So the second term here should be up at 9, and it is. So this graph is matching my first graph here. F of x is equal to 3 to the x power. What about, let's take green. All right, let's look at the second one. F of x is equal to 2 times 3 to the x power. All right, so in this case, it's easy to see, right? This is f of x is y, so y equals 2 times 3 to the x. So now in this case, my a term is 2 and my b term is 3. So if my a term is 2, that's going to be my y-intercept. So I want to look at the 4 graphs here again, and I want to find where is y equal to 2. Well, that's here. So that graph is not going through 2. Here, that graph's not going through 2. But here, it looks like that, yep, that graph is going through y equals 2. And then what I want to do is just double check like we done the first one. If I start with 2, my next term should be 2 times 3, which is 6. All right, so if I move over 1, I should be up at 6, which I am. Okay. And so this graph matches the equation for f of x equals 2 times 3 to the x power. Okay. So that's 2 of our graphs taken care of. Let's look at the next one. So the next one is f of x equals -3 to the x power. So one thing to be careful with, again, this is y equals -3, or sorry, it's negative, this is what you want to be careful of, right? -3 to the x. This is saying -1 times 3 to the x power, okay? If this had been y equals -3 in parentheses to the x power, then we would say the equation is 1 times -3 to the x, okay? But that's not what we're doing here, okay? The 3 is by itself, and so keep in mind your order of operations, right? Exponents first, then multiplication, okay? So for this particular case, we're doing -3 to the x. That's actually -1 times +3 to the x. So a in this case is going to be -1, and b is a factor of 3. So looking at these two graphs that are left, which one has a y-intercept of -1? Right, this one, -1 is here, so that graph doesn't go through there. But this one does. -1 is right there on the graph. Right? And if a is -1, the next term should be -1 times 3, which would be -3. So if I move over one more for x, I should be here at -3, which I am. And if I'd multiply by 3 again, that would be -9, which is the next one here. So this graph does match f of x equals -3 to the x power. Okay. Now the last one. Right, so the last one, we've got f of x is equal to -2 times 3 to the x. So I can write this as y equals -2 times 3 to the x. So here a is -2 and b is 3. So my y-intercept is -2. So hopefully this last graph matches this equation. So my y-intercept, yep, is -2. And the next term in my sequence would be -2 times 3, or -6. So, yep, that one's right there. So that matches. So that means my last graph is f of x is equal to -2 times 3 to the x power. Okay. So this has been just an introduction into what an exponential equation is, how you write it, how you can find it, given points from either a table or a graph. Okay. So just keep this equation in mind, right? Y equals a times b to the x power, where a is the y-intercept and b is the common factor from your graph.